now my honor to introduce our first keynote speaker of this year, Jim Keller.
Yeah, wow, there's quite a crowd in here. This is great. Yeah, whenever I volunteered to give this talk, or a friend asked me, and I always think, sure, that's 6 months away, I'll think of something. And then as it looms up, I start getting stressed out about the talk, because it's hard to focus on one thing, and there's lots of things. And then, you know, what time is it? It's 9 o'clock in the morning. And already like 5 amazing things have happened. So there was an accident on 101, so of course, my little indicator on my trip went from, 40 minutes to an hour and a half, which was a drag. And then some AI program on Google rerouted me, which was super fun. And I was stewing on, if we had autonomous driving, this accident probably wouldn't have happened, which is kind of wild. And then you just talked about Conway and Mead was a phenomenal book. I still remember everybody understands abstraction layers. In college, I studied electromagnetics and semiconductor physics. And then for some reason, I took a job in Florida because I wanted to live on the beach and surf. I was a very serious person at the time. And I did logic design, which is really interesting. And then I went to digital, where I learned to be a computer architect. But when I joined the semiconductor group, it kind of took us back. And the Conway and Mead book kind of bridged the gap between what's logic design and what's a transistor, and how do we map that space, right? Because semiconductor physics is at the bottom, and then there's transistor design, and then transforming that into logic design, and transforming that into higher level design, and then architecture. And as so that was amazing. And then there was a little snippet of Led Zeppelin for some reason. I didn't quite catch how that fit in this meeting, but when I was a kid, I saw them twice. And, right up with the birth of my children, it's one of the best things I've ever done. So, yeah, it's been a pretty good day already. Now it's 9:07. All right, so I've been working at Tenstorrent for 3 years, and before that, I worked at Intel, where we did a bunch of AI. To be honest, though, my job at Intel was mostly about CAD methodologies and transforming how we did IP and CAD and a bunch of stuff, which was interesting. And then before that, it was Tesla, where we built the autopilot chip. And so I've been involved in AI for 10 years, but the last couple of years have been kind of wild, because building AI is another one of these radical transformations, right? AI is not just running a program faster. It kind of is running a program faster, but let's talk about it. Because I was so wrong about how it actually worked. I made so many mistakes. So I was going to title this talk What I Did Wrong, but that seems a little negative. I'm a positive person, so we'll get to that part a little bit. So here's my talk. I'm going to talk about what is AI, some problems we had, what's going on with open source. I will get to what we did right and wrong, and then what's next. And I love this joke. I just died laughing. There's a meta joke behind it, which somebody said, it'll take AI to play chess, but when we play chess, that wasn't AI. But it'll take AI to play Go, but that wasn't AI. And it'll be AI when you could recognize speech, but that wasn't AI. And every time AI does something, it stops being I. And we no longer know what intelligence is. And it's a really wild story. But actually, the story about how we build AI is fascinating. So I worked with Andrej Karpathy for a while. He's a great person, by the way, as well as a really great AI researcher. And he said, here's the map model. So I've been trying to learn to shitpost on Twitter. Yeah, sometimes it works pretty good. It's fun. But if this was the program we had to run, this would be really easy. Right? That's not a very hard program. Like, what's all the drama about? And then I remembered back in 1982, I was working on the VAX 8800, 1982, that's a couple years ago. And the VAX 8800 was a dual processor VAX. And we met with the Fortran group, and they were going to vectorize and then parallelize Fortran. And they had a 1-year plan. and that's not finished yet. And so apparently that was a little harder than we thought. Now there's been some progress. We can vectorize small vectors, and there's some auto-parallelization, but you have to write the code that way. So that's kind of a wild thing. And then part of it's because of this. And one of my misunderstandings of AI was, as a CPU designer, there's a really solid, what we call hardware-software contract, right? The hardware presents a layer to the software that says there is a memory. We do loads and stores for memory in the registers. We do operations on registers. There's a PC that puts in a program. Some of the instructions let you change where the PC is going. And as long as we honor that contract, software can do any damn thing it wants, to the point where hardware designers and software designers don't actually have to talk very much. Does everybody understand that? It's kind of a wild thing. And then people say, well, C programs is like assembly. Yeah, that's like the low level, but you go to C, to C++, to Java, to JavaScript, to God knows what, and they can go do whatever they want. And it's partly because the operations are one thing at a time, and humans think in linear narrative. It's very simple. I'll do this, and I'll do this, and if this happens, I'll do that. That's easy to do, and the operations are essentially all scalar. That makes sense. So this is really simple. So if you start working on AI and you look at a program and you think, well, there's a PyTorch program. That's pretty cool. There's some libraries on the side. We're going to map PyTorch operations to kernels. You know, underneath there, we're going to have to move some data around. It's kind of an extra step, right? So like in Tenstorrent's first computer, we put a hardware data mover because we're going to write kernel libraries. They're called LLKs. We have some data movement. We're going to move stuff around. And then everybody publishes their AI programs. And for some reason, lots of them, when they publish it either as math, which looks very abstract, you know, the sum of the integral of I to the minus 8 to infinity. I don't really know what that's about, by the way, because when they write the code, it all looks like matrix multiplies and data movement in really large arrays. And then the cool thing about these graphs is you can either do sequential operation, which is run one thing at a time, or you can sort of take the graph and lay it out and spread it across chips. So we did a lot of work to take the PyTorch version of this program to create a graph, to spread that across chips, accelerated by fast math and data movement hardware. That seems obvious. And then mysteriously, the actual set of operations there is pretty small. And you would think, what could go wrong with matrix multiply convolutions, tensor modifications, softmax, all-to-all libraries? And I love this picture too, because it turns out you can write all these programs and then somebody else can put them all together in some strange way. But the problem isn't these operations. It's the size of them and the combinations and everything else. And so this is deceptively simple, right? You know, the first thing there is a vector. You know, I Googled these images somewhere. And there's a scalar, which CPUs are great at doing. We added vector units to CPUs, and everybody thought, oh, this code will go 8 times faster. It's an 8-wide vector. And you know, that was a terrible experience. It took 20 years, and not very many things are vectorized. And the AI guys start with a vector, but then they go to a matrix and then tensor modification. And the problem isn't this picture. The problem is these things are 2,000 by 2,000 by 4,000, right? And you have to spread them across lots of chips, and you have to do all kinds of modifications. And what they call the Fortran problem of vectorizing code for that is currently relatively unsolved, right? And we have to do something different, which has been kind of wild. And then there's the interesting thing about how the hell did we get here? So my friend Pushkar Ranade, you know, really likes to study trends of technology, and we were discussing this, and I realized about every factor of 100 transistors enabled a new kind of programming. And this is kind of like a math statement. We had scalar computers, and then it got more transistors, and we got vector processors, and we got more transistors. That led to tensor processors, and I put a question mark there because obviously something is coming next, which is going to be even crazier, right? And so the transistor count enables this deeper math. And then, on scalar computers, we use faster computers actually to run bigger and bigger compilers to solve the compiler side. And we also pour transistors into CPUs to make them faster. We went from single wide to dual wide to pipeline to super pipeline to out of order issue. And each step when we did it was hard, right? And it took many years. Like when I worked on the Alpha EB6 processor back in like 95, 96, 97. And there was a lot of people that didn't think we could ever build a fast out of order processor. Right now, all the high-end CPUs are out of order. We kind of have it cracked. And there was some real technology to build. How do you do registry naming? How do you do instruction numbering? How do you do kills? These are hard problems. How do we build predictors? Now, it turns out once you have a good pipeline in the computer, scaling up register renaming is work, but it's not an invention at some level. And the same thing would happen in predictors. Like once we started predicting instruction streams, better predictors could be researched relatively independently, and sometimes you could just drop that in, right? So vector computers have been around for quite a while. The Cray was a series of computers, and they were pretty good, but hard to program. And then GPUs were invented, and GPUs are a kind of vector computer, which is really wild, because while GPUs have big vectors, they essentially run scalar programs on each element. And you can think of them as running a vector of scalar programs, which, by the way, was a genius abstraction. Because everybody can write a scalar program, almost nobody can write a vector program, but suddenly we had all kinds of people doing vector programs on GPUs, despite the fact that vector programming is impossible, right? Now, that let them build computers with about 5 to 10 times as much math as the CPU. When the AI revolution came along, they had a huge step up. Now, technically, most of AI is not vectors. It's mostly tensors of higher dimensionality with bigger transformations, right? And modern GPUs are hybrids. They have both vector processors in the old style, and then they have tensor units, which do denser math, right? And they haven't really solved the programming problem in the sense that you can't just write a PyTorch program and make it happen, right? Like NVIDIA literally has thousands of people writing low-level libraries, and then the current, let's say, situation is the hardware and software kind of co-evolve together, which is cool. Like, you have a computer and you want to go fast and you write a program that will run on that computer. If you write programs that don't run on any computer, that won't be successful. But it's a complicated stack. And my friend Raja Gadori said, I just want to write a PyTorch program that goes fast. And my brain was going, what are you talking about? Like, a PyTorch program is a pretty simple thing. When you look at it, it says, do a matrix multiply of 2,000 by 2,000, right? And then like invert the matrix or bloat it or shrink it or something. Like, those statements are so easy, right? But that's not the problem. The PyTorch problem is not the right problem. And then I realized I love pyramids, by the way. So the problem is, it's a pyramid of operation rates. Because what the AI programmer wants at the bottom is these unbelievable flop rates, right? So you build a big matrix unit. Ours does 4,000 operations a second. It's a big number, by the way, right? And then filling that automatically is almost impossible. So you have to write, you have to issue math instructions for that. It's not 4,000 math instructions like old CPUs would have been. It's a one math instruction. That's 3 orders of magnitude of operations. And then we issue kernels on each AI processor, and then at the chip level, we dispatch kernels to all the processors. And then at the PyTorch level, it's kind of clunking along. And above that, there's, in a data center, you might see somebody doing data parallelism or model parallelism. Like, you might manage that at a higher level. And this picture only recently occurred to me, unfortunately. This would have been a really good thing to start a startup with. Like, I understand every single layer, and for some reason, humans can tolerate a factor of 100 to 1,000 step up in complexity, right? And if you skip one of these layers, what you end up having is a very large team programming around the problem, which is kind of a wild thing. So the PyTorch program, unbelievably, today, everybody knows this is 2024, is running at hundreds of Keller. That's really hundreds of kilohertz. The PyTorch instruction rate on a supercomputer is 100 kilohertz, which I didn't really realize until recently. Now, each operation is really big, and it just gets dispatched to lots of chips, and then it gets pushed down the funnel, because at the bottom, you're going pretty fast. So that's a fun. Who knew? So we, like a lot of people, took PyTorch programs seriously, and then we wrote a compiler for them. We knew at the bottom you needed a big math engine, the data movement, but we started building our way down, right? And the problem is you build your way down, you get lost on the way, and then somebody told me this is a quote from Chris Latner, who's a really good program. He did C++, or LLVM and Swift, and now he's building Mojo. He's done a couple other like amazing projects. MLIR, he built that. And he said one of his goals was, first you make fast kernels and you prove that they work. And then you make sure they're generatable by some other human. So this is a real common problem in vector programming. Somebody can do it, but nobody else can, right? Then you prove you can generate that with a compiler. And then you make the compiler that generates it. And that's still currently the hard step. So we wrote a new software layer, which is kind of above the low-level kernels, but it's in an intermediate layer where we can easily write very fast, very large operations and chain very fast operations together. And it's a right kind of abstraction level for a human being, which is kind of in the millions to 10 millions of operations a second to coordinate that. So I was told by many investors and people about how complicated AI is, and CUDA's a moat. And I responded that CUDA is actually a swamp, not a moat, technically. Like, a moat is like a pool of water that's clean. A swamp is a hard territory to traverse, right? And possibly because it's muddy and wet. But we were looking at all these programs, and it turns out most of the AI programs that we had written, you know, there's a lot, you know, Mistral, Falcon, Llama, ResNet. Stable Diffusion's big. They were all 600 lines of code, right? Now, at what level, right? There's 600 lines of code at that level of PyTorch, and maybe a click down where we manipulate these objects, right? And then as you go down further, you end up with thousands and thousands of lines of code. Like PyTorch amazingly defines some 300 low-level kernels. And some of those kernels are like a couple hundred lines each. Like at least in our code, we think it's pretty good. So we have this wild thing where AI is a super hard problem. There's huge piles of code to do it. And yet when you actually express the models, it's pretty small. And then here's an example. So we've open sourced our bare metal stack and our compiler. So we have a top-down compiler which does really cool transformations. And then we built a bare metal stack which lets you go from the low-level math kernels and click your way up. And this is, you know, the top of a Llama program. It's like 600 lines of code. Stable Diffusion is really fun because there's an image model in it, a language model, a backpass from training. It's generative. So it's got like 4 different things going on. But it's not very big, but it's complicated. All right. So I'm really interested in how computers work, right? Like normal computers, we know what they do, right? They sequentially execute instructions and modify data, and over time you modify all the data. And then you look at your brain and you think, there's something really amazing because your brain kind of technically thinks, like, but it's very obvious neurons don't think, right? So something happens between those. And then the brain has a really particular organization. The top number is theoretical. Google it. Like there's people who say it's bigger and smaller, and there's a small subset of people who say we're smart because of quantum something or other. So I doubt it, by the way. I don't think thinking is magic. I think thinking is computation, right? But your brain runs at a speed around, 100 to 1,000 hertz, right? Which is really low. Surprisingly, that actually matches the operation rate that data centers run at. Like when you're doing token generation, it's running at, 100 hertz. So we have this wild similarity, which is our current AI programs clunk along at about 100 hertz, as does your brain, right? But somehow marshals computation at an extraordinary rate. And then your brain is technically organized in cortical columns. There's some variation on what people think about that. But there's something like 2 million cortical columns in a human brain. If you do the math, that's about a half a teraop computing. And I was reading about this one day. And brains are mostly local compute, so a cortical column has 6 layers of neurons. Each layer is an all-to-all connection, which looks a lot like a matrix multiply, to be honest. And then they locally talk a lot, but then they globally talk some. And your brain has very good communication methods. So it doesn't look like a network, like the one sends a message to the adjacent one and goes. You have short neurons and very long neurons. But sometimes a short neuron intermediate path will activate a thing, which will then activate a thing. So our brain seems to do both. Local communication and hop-by-hop communication as well as global communication. And then our Tensik AI processors that we build, I noticed we're about 5 teraops, which I thought was hilarious. So we're targeting the same total computes. We're building building blocks the same way. We have adjacent compute, and it's how AI computers are built, apparently. So let me just walk through this a little bit. So we build, it looks small, right? So we built something, basically a tensor processor, which has a big math unit in it. We don't actually have a GPU. GPUs, I think, were an intermediate step. And all AI processors, like TPUs, were announced in 2015, which is a very large tensor processor. I think technically they're too big, in my opinion. So the problem when their processors are too small, there's too much communication. If they're too big, you have to drag the data across them when you don't want to. So there's a just right Goldilocks spot, which I think we're good at. And then we build arrays of these processors. So you can have, and they talk to each other really well, but sometimes you have to talk to the whole chip. And so we have big buses to do that. And sometimes you go hop to hop through the cores, and sometimes you do broadcast. And then you can put multiple of these chips together. And then as you kind of zoom out, it's always the same. It's an array of arrays of arrays, essentially. And the challenge is how do you program that? Because that gives you the best computer density. And you have to do it at each level carefully. And then there's a bunch of really interesting trade-offs. So AI chips have to be big enough to solve problems. So computation for matrix multipliers goes something like n-cubed operations for n-squared data. So as n gets bigger, the computation, like to each other, gets actually smaller, which is pretty nice, right? And there used to be something called Rent's rule or something, which is like the I/O of a chip was proportional to the square root of the number of transistors on the device. So as the devices got bigger, while the bandwidth of the device went up, it went up slower than the transistor count, which is really true. On the flip side, you have to have enough peripheral area. So I worked on a couple wafer scale and large package scale things. And there's a funny thing, as it gets bigger, your ratio of periphery to compute actually gets worse. And if you need a lot of I/O and memory bandwidth, you actually can't get it. So I like wafer scale computing. It doesn't have a good ratio. It gets too big. And then you run into all these nonlinear scaling problems, right? So, I remember when cooling 50 watts was hard, and I used to think, well, what's so hard about 50 watts? The light bulb in my office is 50 watts. It can't be that bad. It's like, right? But, and it turns out, if you look at the flux density of heat through silicon, 50 watts per square centimeter is not bad. You can do 100, but it starts getting pretty sexy technology-wise to go past that. So power delivery has that problem, cooling has that problem, and to date, like HBM DRAMs have that problem. The stacking, the yield of the stacking is complicated and expensive, and it goes on an expensive package. And then you get this problem where, as quantity goes up linearly, cost goes up exponentially. And, I don't think that's the right trend for computing, right? And this is another observation, which is wild. We'd like to think about, we went from mainframes to mini computers to workstations, PCs to mobile, right? That's a transition. And every one of those was on the order of 10x cheaper, right? Now, the rate of that was about every 10 years. And transistor Moore's law generates about 10x more transistors every 5 years. So for every 100x in more transistors, we traded the transistor count for the cost point, right? So that's where we get, I think it's Bell's law. Like every 100x in transistors gives you a new generation of computer. So AI is really wild because we got enough to do transistors, or not transistors to do AI, but at the HPC supercomputing kind of point, right? AI didn't follow mobile as another trade of transistor count for something. It was explosive, which is unheard of. But the other observation is in each of the genres, mainframe, mini workstations, while they were a step change cheaper than the previous generation, in their own life cycles, they got more expensive, right? And this is the temptation of technology. If what I have is good, more of it in a denser place is better, and you'll slowly build yourself something very expensive. So I've been really interested in building low-cost computers, right? I think ultimately AI will get very cheap, right? I hope it's in all the cars, so there's less accidents, less people get hurt. So we built these processors, which are built out of arrays of AI processors, and then we hook them together. This is a picture of 4 Galaxy boxes hosted by a couple of AMD servers, and it scales pretty cheaply. And one thing we're careful about is how much power do we put in a given place? How much memory do we need in a given place? So when we put it together, it stays cheap. Like as it scales up, it doesn't get more expensive. It actually stays the same. So this is let's say, an attempt at linear cost with linear performance. And we think it's going to work pretty well. All right. The second thing I wanted to talk about is openness in AI. So as people have noticed, AI is getting unbelievably valuable. I was joking a couple of years ago, I didn't think GPUs were the way to go. Because people would ask me, like, why don't you just build a GPU? It's like, well, GPUs are a stepping stone to tensor processors, which are going to, so now NVIDIA's worth $3 trillion, which is amazing. But actually more amazing is the openness of what's happened, right? The most valuable software in the world is open. Linux, GCC, MLIR, like we've been watching that every year. It's starting to become used in everything. It's getting built into the infrastructure for PyTorch and JAX. A lot of the high-end AI models are open sourced. RISC-V is an open source processor architecture. And the observation is once something becomes open source, it typically doesn't go backwards. And it's been an unbelievable value creation and sharing of everything. And I'm really fascinated by this. So we started noticing that we open sourced our compiler and our bare metal stack, and some people said, well, as a startup, you can't do that. That's your secret sauce. And I thought, well, Linux is open, GCC is open, LLVM is open, PyTorch is open. Most of the models are open. And I talk to people all the time, and they want to do research in an open environment. They want to publish their work. They want to share it. But the really fun thing that happened is people came to us like for interviews, having already gone through our repos. And in the interview, they're very opinionated about how we wrote code and we did this, but it was a really nice conversation because the code's not secret. It's not a dumpster fire somewhere. If you want to look at it, you can just look at it. We had an investor hire a couple of programmers to go through our code, and then he wanted to make an investment. Like that's never happened to me in my life. That's just amazing. But the intriguing thing is how people respond to openness and what they do, which I really like. So we started open sourcing stuff. So we opened our Our compiler we call Buddha, our bare metal stack. We talked to a whole bunch of students in the last couple of years. And so all the computer architecture students now study RISC-V. And that's because it's open. Berkeley, Dave Patterson, Christy, they did an amazing job of open sourcing RISC-V. Like it's literally scorched earth at the university. So we were like, hey, we're going to open source a vector unit, we're going to do this. And they said, well, Jim, actually, we already have processors, and we can already do that. What we really want is test infrastructure. So we released some architectural tests. We support the Whisper reference model. We just open sourced a new version of the architectural instruction checker. Go check it out, it's online, which is pretty good. So as you make modifications to the RISC-V architecture, which students like to do, they want to do experiments, they can go back and test what they did with open source stuff that's validated. So that's really amazing. The RISC-V CPUs are kind of wild because, so we build a processor we call the baby RISC. It's a little tiny 32-bit processor, and there's 5 of them in every AI engine we use. And then we added a vector unit to that. So we have a big, huge math unit. And then on the side, there's a little vector unit because some of the programs that get dispatched in the AI have all kinds of ugly code paths in them. And so when you're dispatching kernels, you don't want to really be worried about, hey, this kernel only runs on the host somewhere and this only runs somewhere else. So we've made the stack relatively uniform. We use the Rocket Core in our new processor, which is open source by Berkeley. We've used Sci-Fi's X280, it was a great CPU, and our black hole chip. We may or may not use that, or we might go to the Boom Core on the next generation. And then we're building a big 8-wide out of order issue processor, partly for our products and partly to tentpole the RISC-V architecture and to make sure RISC-V has a stack top to bottom, which I think is pretty good. And then translating back to that stack, right, there's this hierarchy of computation. So on some data center processor, we currently use AMD Zen processors. At some point, we'll use Escalon for that. In our next generation, we're putting an array of Escalon processors next to every AI chip. We don't need a lot of them. It turns out, because of our hierarchy of compute, we can scale each one at the right rate. And then on chip, there's an array of X280s on our black hole chip. Next one, we might go to Boom, that do all the chip level dispatch. And then inside every processor, there's somebody issuing the kernels. And then there's a whole bunch of little, army of ants doing the actual execution. And then we have a big math array, which looks like a systolic processor or something. And it's kind of wonder the number of processors as you go down the stack. Somewhere in the data centers, 256, way down in the computers. This is for like 128 chips. It'd be 64,000 little processors. So the vision of I have a PyTorch computer, right? There's what looks like a single-threaded PyTorch program, or maybe a small array of them dispatched to multiple computers, but really sensible and easy to understand. Running at relatively low instruction rates, which is kind of wild. Dispatching to computers, there's thousands of them running at multiple petaflops. Like, that's a wild thing. Okay. So what doesn't work? Like, I posted this online because sanity is hard to achieve, right? And like Cerebrus guys, I've always loved them. They've never been ported at sanity. NVIDIA has become obviously way more expensive, good for them, making lots of money, but I don't think that's the right rate. And AMD decided to chase them instead of chase sanity, so we'll see. And we screwed around for a while, so that's how it goes. The hardware-software contract is so different that you have to really reconceptualize it, right? It's not one contract, it's many. And as you go down the stack, it's not one runtime environment, there's many. The top-down compiler stuff doesn't work. It's been really difficult. Periodically, I hear of a project like we're gonna auto-parallelize PyTorch, and I think, no, you're not. That project's been going on for over 50 years, and I don't see what's going on. I doubt putting too much in a package is a good idea. This has been tried many times. Does anybody remember Power 5? I love that computer. Power 4, Power 3, Power 4, Power. They pushed the envelope of packaging and technology. Power 5 Server shelf was like 100 kilowatts. It was amazing, unbelievably expensive. They didn't sell any. Tricks generally don't work, and this is one of those things because hacks do. And by trick, I mean you have some, quantum computing or, something or other, right? Now, in the gaming world, and GPU guys know this really well, right? There's architectural work, like what's game engines look like, what's the GPU look like, what's the next step for DX, for OpenGL, right? And then they build software based on that. But when you open up the magazine, you see the top 10, games benchmarked by PC Week or something. Those are all hacked, right? They publish the game, and then the team goes to work. Like, they call this library a lot. After this library, let's make a fused kernel so we don't bounce back and forth. The way this data is laid out is like this. We're going to go hack the code. And then the top 10 games are all hacked, right? And then every once in a while, somebody will complain on the forum that the new release of the NVIDIA driver slowed down Call of Duty 0.1 by 10x. And that's because they took the hacks out, right? When it stops being in the top, you can't, that's technical debt, right? But tricks don't really work either, right? Like AI is a bread and butter, high-end computing problem. Flops, knock bandwidth, memory bandwidth, I/O bandwidth. And we worked on stuff like conditional execution, hardware compression, hardware data movement. Most of that didn't work. Most claims, every once in a while, I get called by VCs for due diligence, and some company has a 100x faster approach. I don't think so. There was a paper recently, 1-bit computing solves all problems. We'll see. I don't think that works. I think what really works and what we're really happy with is really solid semiconductor execution, really strong math units, NOCs, all the details of design, and then really bottom up layer by layer, prove every single layer, works really fast. This next one is a really solid split between the runtime and the compiler. When you build an elaborate compiler environment, it impacts how you think of the runtime environment, right? Like in CPUs, we also have kind of a wall there. How you compile the code and how you run the code are really separate in the compiled world. In the JITted world and the just-in-time world, they often get conflated. But AI programs, especially big ones, run really optimized. We've mostly gone at the bottom to sequential operation. That means take very large operations, flood as many chips as you can, run them really fast. But there's a really cool thing, which is we can lay out layers of computation across lots of processors, and then the next layer is in the same place, and the data stays put. And so it's sequential, but cortical columns in your brain work that way. We have 6 layers of neurons, and you compute sequentially down through those layers. I think we made a great choice on Ethernet. It's the lowest cost transport with the best PHYs, right? All the tricks, Rocky, InfiniBand, Ultra Ethernet. It's not really changing the fundamentals, which is how do you go really fast with transport. And then I think open source has been great. And we learned a lot. And open sourcing your code base and stuff, and we open sourced the vector unit for RISC-V, we open sourced instruction test. You always wonder when you open source it, are people going to hate it? Is it stupid, a waste of time? But then you get feedback and people call you. And we got some pull requests to improve our documentation. Super fun. So you can't make that stuff up. It's great. All right, what are we doing next? So we've built a really fast backend. We have a good compiler. The MLIR stack is really fun. So we're going to build an MLIR layer, both to interface our really fast backend with our compiler, and then also interface that into JAX. We have a lot more models and ops and transformations to do. I want to be much better at interfacing into the open standard software. And it's amazing how much software there is. It's really quite complicated. But it's mostly, how do you interface to a program? How do you interface to models and kernels? How do you manage processors? It's a really interesting thing. It's not auto-vectorizing math for the most part, although there's many projects working on that. And then we're building better debug tools. I told our debug team is, I want a single step, 1 million CPUs. Tick, tick. If everybody had been in the lab single stacking a computer that doesn't work, It's super fun. But we're going to single step 1 million little processors doing petaflops of computation. So I've made that a personal goal. On hardware, our chips up to now have been, monolithic chips. Our next generation, this is pictures. These are artist conceptions of the chiplets. We're breaking this up. It's partly for configurability. Partly it kills me. We're building a chip where we're repurchasing, very expensive IP and putting it down in exactly the same way. I want to disaggregate the chip a little bit, and the packaging supports that. Our black hole chip, we went to 400 gig. We're going to 800 gig. We're looking at much faster memory, more compute in the stack. Really big thing is cleaning up the programmability through each layer. I would really, really like our hardware to be published with a proper spec so that other people could write a low-level bare metal stack. I think that's doable. We're getting really close. And then we're thinking about more releases of open source, both hardware and software, and we're working with a number of people on how to do that. Because the open source stuff is really wild. The energy in it is fantastic. All right, here's the summary. I thought this was a sunrise photo. We just powered this chip on. It was really fun. So we were doing some fundraising, and we decided while we were fundraising to open source software, publish some high performance models and power on a chip. And I thought, well, it's one of the dumbest plans I've ever heard, but so far it's been pretty successful. This is a sunset photo of the chips in the lab. The team was really, building silicon is great. Is there anybody here involved in building silicon? It's so much fun, right? And there's the part of the process where you're thinking of ideas and you get in execution mode and then you tape out. And the way tape outs work now is you have a couple months to build up your anxiety because you've just spent $50 million possibly, or last $50 million, to go build a chip which might not work. It's like, hey, honey, I spent $50 million. Well, someday it's going to work out. But then you power it on, you find a problem, you work around it, things come up, works pretty good. It's unbelievable. So I'm super happy with the open source we've done. And then I really want to keep working on this hardware-software contract for AI, which is how do we get the hardware and the software to play together? And it's been quite a wild ride for the last couple of years, but it's been really great. And that's my talk. All right, thanks, everybody.